With the help of technology, man is exploring the space. We know a lot about the different planets, our own sun and the stars. But it is rather very intriguing that we do not know even half as much of what we know about the space regarding our own Earth. I am talking about the limitation of our knowledge regarding what is happening deep inside the Earth, maybe a few hundred kilometers below our feet. The scientists have proved that Earth has a layered structure, and these layers are actually concentric zones. The innermost such concentric zone is called the core, possibly the most inaccessible part of the Earth, and possibly man will never be able to reach there. To understand the core, if we answer 5 small questions, we will get an idea about our present state of knowledge on the core. The first question, the most fundamental one, what is the core? Second one is even more challenging. How do you know that there is a core? The third one is, if it is so remote, is there any way that we can know about the composition of the core? The fourth one is, how did it form? And the final one, when did it form? By answering these 5 simple questions, we plan to understand the core. So the first question, what is the core of the Earth? We know from different means of studies, of which one of the most important means is the study of earthquake waves, that Earth has a layered structure. It is made up of 3 concentric layers. From the surface to the center of the Earth, these 3 layers are respectively the crust, the mantle and the core. The crust is the place on which we all live, and it is only about 40 kilometers thick. From there, that is the 40 kilometers to a depth of 2,891 kilometers is the zone that is called the mantle, and from 2,891 kilometers to the center of the Earth, that is at a depth of 6,371 kilometers, is that zone called the core. These 3 zones differ from each other in their physical properties as well as in chemical properties. The boundaries between these zones are called discontinuity surfaces, because the waves generated by earthquakes show very sharp jumps in their velocities. The core itself has 2 layers, one extending from 2,891 kilometers to a depth of 5,151 kilometers. That zone is called the outer core, and from there, that is 5,151 kilometers, to the center of the Earth is the inner core. Core is a very exciting place, and in the sense, core has a temperature, especially the inner core, which is comparable to that of the sun, that is very close to 5,000 degrees Celsius. Core is a zone of very, very high pressure, which is about 200,000 times that of the pressure that we experience on the surface of the Earth. So it is a very extreme situation that the core is very difficult to understand. The reason is that any material changes its behavior when it is put to such a high pressure and high temperature. Now there are many means in which we can study the core. The most 3 important means are the use of waves generated by earthquake. We call them seismic waves. A few other important facts about the core is that across the boundary between the mantle and the core, that is at a depth of 2,891 kilometers, there is a huge jump in density of the material. The density jumps from nearly 6 grams per cubic centimeter to about 10 grams per cubic centimeter. More interestingly enough, within the inner core, that is the solid innermost part of the Earth, the density jumps to up to about 13 grams per cubic centimeter. So as we go inside the earth, the pressure increases and the materials become denser and denser. The challenge is that we do not know very many substances on the surface of the earth that can give some high densities like 12 and 13. So it becomes more and more difficult to understand the nature of the core because the materials behave differently at that high pressure. The another factor that complicates our understanding about core is the very, very high temperature that is comparable to the surface of the sun, anywhere between 5000 degrees Celsius to as high as 6000 degrees Celsius. With this background in mind, let us answer the question, how do we know that there is a core? There are three different ways in which we try to understand the nature of the core and thereby can prove the existence of the core. Three different methods that are used are those using the waves generated by earthquakes, the geochemical and cosmochemical properties of the earth and its comparison with the other members of the solar system, that is the planets and also the sun itself, and finally by evaluating the physical properties of the earth as a rotating solid mass. The first method is the method using earthquake waves. Earthquakes are also called seismicity, that's why earthquake waves are called seismic waves. Before we go into the details of this method, it will be nice to understand what is an earthquake. Earthquake refers to vibration of the ground when two different blocks of rocks move past each other along a surface. Because of the energy released for the formation of the fracture along which the rocks move and the frictional resistance that has to be overcome by the movement of the block, huge amount of energy is released. It is the part of that energy that destroys the civilization. But earthquakes bring good news to many scientists because the earthquakes generate waves by means of which the energy travels to the interior of the earth. They can travel through the entire diameter of the earth and can be recorded at the surface. This is more like the X-ray that the doctors use. The doctors use the X-ray to see what is inside the body without even damaging it. In the same fashion, earthquake waves generated by earthquakes travel through the earth, and when they travel through the earth, they record the change in the properties of the medium through which they travel. These waves are recorded by an instrument called seismograph, and the record of the travel and the changes the earthquakes has to go through because the changes of the medium through which they pass are called seismograms. It is the study of these seismograms reveals astounding information about the internal structure and composition of the earth, and the discovery of the core to a large extent is dependent upon these earthquake waves. When an earthquake takes place, two major kinds of waves travel through inside the earth. These are called primary or P waves and secondary or S waves. The velocities of these waves are dependent upon three factors or three properties of the medium through which they pass. The important factor that controls the velocity is the density of the medium. As the density increases, the velocity of both P waves and S waves decrease. In addition, P wave velocities varies directly with the sum of two other properties of the medium, namely the bulk modulus and the rigidity modulus. P waves increases when the sum of these two moduli increase. The bulk modulus is an expression for change in volume of an object when put under stress. Rigidity modulus is a measure which tells us how difficult it is to change the shape of an object. The more the rigidity modulus, it will be more difficult to change the shape of the object. Contrary to the p wave velocities, s wave velocities have only two controls. As the density increases, s wave velocities drop, and if the rigidity modulus increases, the s wave velocity will increase. The thing to note is that because the rigidity modulus controls the s wave velocity and there is no contribution from the bulk modulus, if the rigidity modulus of a medium becomes equal to 0, the velocity of s waves also becomes 0. Liquids do not have the property to retain its own shape. Therefore, it has a rigidity modulus of 0. As a result, s waves cannot pass through liquid. This is a very important tool, that p wave can pass through liquid, but s wave cannot pass through liquid, is of great importance in understanding what is the nature of the outer core. That means the zone that extends from a depth of 2,891 kilometers and 5,151 kilometers. Now let us take a look at the historical development of our ideas regarding the core. In 1906, a British geologist, Oldham, was studying the earthquakes generated in different parts of the earth, and he found that after reaching a great depth, the velocities of the earthquakes, especially the p wave velocity, drops drastically, reduced from about 13 kilometers per second to about 8 kilometers per second. He attributed this vast drop in the velocity due to the change in the density of the material along a discontinuity surface. In 1913, Gutenberg, a German seismologist, calculated that depth to be very close to 2,900 kilometers. Present technology has revised this depth to 2,891 kilometers, and the existence of a highly dense material at that depth was established. That there is a break even within the core, that is the boundary between the inner core and outer core, at a depth of 5,151 kilometers, was established by Inge Lehmann, a seismologist from Denmark. She was studying the seismograms to find what is the reason for, again, a jump in velocity at a depth of 5,151 kilometers depth. In addition to the velocities directly observable and calculated in the seismograms, she used a property called polarization of earthquake waves. By the phenomenon of polarization, an earthquake, when travels from one medium and comes in contact with another medium with a velocity different from the previous medium, the wave splits into two waves. That is, a p wave will split into a p wave and an s wave, and the s wave will split into again a p wave and s wave. Using this phenomenon, Lehmann proved that after the depth of 5,151 kilometers, s waves can travel through the central part of the earth. Thereby, she proved that the central part of the earth, the inner core, is solid.
Please watch next part of the program, Core of Earth Part 2.